Recall that what fitting a linear regression does is minimize a loss function to choose a coefficient AI for each feature variable. If we allow these coefficients or parameters to be super large, we can get overfitting. It isn't so easy to see in 2 dimensions, but when you have loads and loads of features, that is, if your data sit in a high-dimensional space, with large coefficients, it gets easy to predict nearly anything. For this reason, it's common practice to alter the loss function so that it penalizes for large coefficients. This is called regularization. The first type of regularized regression that we'll look at is called ridge regression, in which our loss function is the standard OLS function plus the squared value of each coefficient multiplied by some constant alpha. Thus, when minimizing the loss function to fit to our data, models are penalized for coefficients with a large magnitude, large positive and large negative coefficients, that is. Note that alpha is a parameter we need to choose in order to fit and predict. Essentially, we can select the alpha for which our model performs best. Picking alpha for ridge regression is similar to picking K in KNN. This is called hyperparameter tuning, and we'll see much more of this soon. This alpha, which you may also see called lambda in the wild, can be thought of as a parameter that controls model complexity. Notice that when alpha is equal to 0, we get back OLS. Large coefficients, in this case, are not penalized, and the overfitting problem is not accounted for. A very high alpha means that large coefficients are significantly penalized, which can lead to a model that is too simple and ends up underfitting the data. The method of performing ridge regression with scikit-learn mirrors the other models that we've seen. We import ridge from sklearn.linearmodel. We split our data into test and train, fit on the training and predict on the test. Note that we set alpha using the keyword argument alpha. Also notice the argument normalize. Setting this equal to true ensures that all our variables are on the same scale, and we'll cover this in more depth later. There is another type of regularized regression called lasso regression, in which our loss function is the standard OLS loss function plus the absolute value of each coefficient multiplied by some constant alpha. The method of performing lasso regression in scikit-learn mirrors ridge regression, as you can see here. One of the really cool aspects of lasso regression is that it can be used to select important features of a dataset. This is because it tends to shrink the coefficients of less important features to be exactly 0. The features whose coefficients are not shrunk to 0 are selected by the lasso algorithm. Let's check this out in practice. We import lasso as before and store the feature names in the variable names. We then instantiate our regressor, fit it to the data as always. Then we can extract the coef attribute and store it in lascoef. Plotting the coefficients as a function of feature name yields this figure, and you can see directly that the most important predictor for our target variable, housing price, is number of rooms. This is not surprising and is a great sanity check. Now, this type of feature selection is very important for machine learning in an industry or business setting because it allows you, as a data scientist, to communicate important results to non-technical colleagues and bosses. The power of reporting important features from a linear model cannot be overestimated. It is also valuable in research science in order to identify which factors are important predictors for various physical phenomena.